Hello, in this lecture we'll answer two questions. In the first question we'll find out the area of this circle, and in the second question we'll find out the area of trapezoid ABCD. Okay, so we'll start with the first question. In the drawing we have a circle, and this is the current side point P. From this current side point P we have two tangents to this circle, tangent PA and tangent PB. In addition we have the right angle ACP. The right angle ACP cuts the circle at 2 points, point A and this point. This is the angle ACP, that is the right angle. Side CP of the right angle ACP equals to 4 units in its length. This is line 7 VC, that is equals to 1 unit. And our mission is to find out the area of this circle. So here we can implement rule 2. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents for a common side point. The length of two tangents for a common side point for a circle are equal. So in the drawing we have a circle, and this is the common side point P. From this common side point P we have two tangents to the circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. In our drawing, from this common side point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So I write it down. PA equals to PB according to rule 2. It is given as the question that the length of tangent PB in total it is equals to 4 plus 1, that is 5. So we can write that PB equals to 5. And from this equation PA equals to PB equals to 5, we will derive that PA is also equal to 5 units in its length. And this is PA, that is equals to 5 units in its length according to rule 2. In the next step I will copy the right angle ACP in a new page, and we will implement the Pythagoras theorem on this right angle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the evaluation for Pythagoras theorem. Okay, this is the right triangle ACP, that is the code from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. So I write it down. AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25, and it is equals to AC squared. AC is the missing side, so we leave it as it is. It is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we should find out the 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and we get that AC squared equals to 25 minus 16 is 9. So AC squared equals to 9. Here we take a root out of this equation, and finally get that AC equals to the square root of 9, that is 3. So if we found out the length of the missing side AC is 3 units. We can write here that AC, this side AC, is equals to 3 units in its length. AC equals to 3. In the next step, we define the center of the circle. This point is point O. And we also define the radius of this circle as x. So in the next step, we join points O and B together by a straight line. What is the definition? What is the definition of line segment OB? Line segment OB starts from point O, that is the center of the circle, and that's at point B, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OB is the radius of the circle, is equals to x according to our definition. So here we can implement rule 1, or pick on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius known to its point of tendency. So in the drawing we have a circle, and this is tangent AB, and the tangent to this circle is point M. And here also the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And remember, your radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Right, so in our drawing we have the radius OB, that is equals to x. The radius OB of this circle is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever your radius is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us the question that PB is a tangent. So PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point C here, so here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side of the straight line PB is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say, from this point O, that is the center of the circle, we will go perpendicular on AC. So if this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, we can do quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this four facing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this four facing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 rectangles. And according to rule 5, it says that any quadrilateral that has 4 rectangles must be this rectangle if not a square. So we relate to quadrilateral OECB as a rectangle because it has 4 rectangles. So quadrilateral OEBC is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OECB, side OE must be equal to the opposite side CB. But CB is 1, therefore OE must be also equal to 1. Likewise, according to the sum rule, in the same rectangle OECB, side OB must be equal to the opposite side CE. But OB is x, therefore CE must be also equal to x. What is the length of this line segment AE? From the drawing, it is very easy to see that AE equals to AC minus EC. Again, AE equals to AC minus EC. So write it down. AE equals to AC minus EC. So AE equals to AC, that is 3, minus EC is x. So in total, AE equals to 3 minus x. AE equals to 3 minus x. The next step, we will join points O and A together by straight line. What is the definition of line segment OA? Line segment OA starts from point O, that is the center of the circle, and that's at point A, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OA is the radius of the circle that is equals to x according to our definition. In the next step, we'll copy the right main triangle OAE in a new page, and we'll implement the Pythagoras theorem in this right main triangle OAE. Here by PT is the evaluation for Pythagoras theorem. So actually, this is the right grand triangle OAE that I got from the original drawing. According to the Pythagoras theorem, in this right triangle OAE, OA squared, that is the square of the hypotenuse, equals to AE squared plus EO squared. So write a note. OA squared, that is the square of the orthogonal, equals to AE squared plus OE squared. The hypotenuse AO is x, therefore AO squared is x squared, and it is equals to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared, plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total we should find out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x, plus 1. So here we have x squared on both sides of the equation, so x squared will be cancelled. After cancelled x squared on this side of the equation we left with nothing, that is to say 0, equals to 9 plus 1 is 10, minus 6x. So in total we found out that 0 equals to 10 minus 6x. Here we add 6x to this equation, and we get that 6x equals to 10. Here we divide this equation by 2 and finally get that 6x over 2 is 3x equals to 10 over 2 is 5. So 3x equals to 5. Here we divide this equation by 3 and finally we get that x equals to 5 over 3. So if I found out that the radius x of this circle is equal to 5 over 3 units in its length. Our mission is to find out the area of this circle. The area of any circle equals to pi times the radius of the circle squared. So I write it down. The area of any circle is equal to pi times the radius of the circle squared. Therefore the area of our circle will be equal to pi times the radius of this circle squared. The radius of this circle is x. Therefore the radius squared is x squared. So in total we found out that the area of our circle is equal to pi x squared. So it is pi times x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. So the area of our circle in total it is equal to pi times 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total we found out that the area of this circle equals to either 25 pi over 9 square units, so in terms of numbers the area of this circle is equal to 8.727 square units. So nothing wrong. 8.727 square units. Repeat again, we found out that the area of this circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of this circle is equal to 8.727 square units. So we finish with the first question. In the next step, we'll present you the second question and we'll solve this. Our mission in the second question is to find out the area of this trapezoid ABCD. It's given us the question that side AB equals to 16 units, AD equals to 17, BC equals to 25, and side DC equals to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. The area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. Therefore, the area of this trapezoid ABCD will be equal to the sum of its two parallel bases. The two parallel bases are AB and DC. Therefore, it is AB plus DC times the height, that is h over 2. Okay, found out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is H, over 2. The height H must create 90 degrees with the two parallel bases. That is to say, it must create 90 degrees with AB and DC. So in order to find out the area of this trapezoid ABCD, we do a construction. That is to say, from this point A, we will draw perpendicular on DC. Okay, again, from point A, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. We define the side of DE as X, and we define the side of AE as H. H is the height of trapezoid ABCD. Why H is the height? Because H creates 90 degrees with the base DC. Therefore H is also the height of trapezoid ABCD. So in the next step, I'll copy the right triangle ADE in a new page, and we will implement the Pythagoras theorem on this right triangle ADE. Here by PT is a proportion for Pythagoras theorem. So actually, this is the right triangle ADE that is going from the original drawing. According to the Pythagoras theorem, in this right triangle ADE, AD squared, that is the square of the hypotenuse, equals to AE squared plus DE squared. So I write it down. AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289, and it is equals to AE squared. AE is H, therefore AE squared is H squared, plus DE squared. DE is X, therefore DE squared is X squared. So today we found out that according to equation 1, H squared plus X squared equals to 289. in the next step we will do another construction. That is to say, from this point B, we will go perpendicular on BC. But again, from point B, we will go perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B and DC. This point is point F. We know that side AB is parallel to side DC. So those two angles are located between the parallel lines AB and DC, and therefore they are defined as center angles. In addition, those two angles, they are both located on the right side of AE. Again, those two angles are both located on the right side of AE, and therefore they are both defined as one-sided because they are located in the right side of the straight line AE. So in total, those two angles, they are defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So repeat quickly on rule 16. According to rule 16, the sum of one-sided interior angles is equal to 180 degrees. So in the drawing, we have two parallel lines. That is to say, line A is parallel to line B, and you have line I that cuts the two parallel lines A and B. So those two angles, they are both defined, that is to say, angle 4 and angle 5, they are both defined as interior one-sided angles, and according to this rule 16, the sum of those two angles is equal to 180 degrees. That is to say, angle 4 plus angle 5 equals to 180 degrees. Likewise, those two angles, actually the angles 3 and 6, they are both defined as one-sided interior angles, and according to this rule 16, the sum of those two angles is equal to 180 degrees. That is to say, angle 3 plus angle 6 is equal to 180 degrees. Okay? So we can actually implement rule 16 in our drawing. Why? Because in our drawing, I already explained that those two angles, they are both defined as one-sided interior angles, and therefore according to rule 16, the sum of those two angles is equal to 180 degrees. So this angle is equal to 90 degrees. The missing angle is angle ABF, and the sum of those two angles is equal to 180 degrees. So I write it down. So this is the missing angle ABF plus this angle, that is the right angle. In total, the sum of those two angles, is 180 degrees, according to rule 16. Repeat again, according to rule 16, the sum of the missing angle ABF plus the right angle, in total, must be equal to 180 degrees in their sizes. According to rule 16, here we subtract 90 degrees from this equation. and we get that the missing angle ABF is equal to 180 degrees minus 90 degrees is 90 degrees. So she found out that the size of the missing angle ABF, the size of this missing angle ABF is equal to 90 degrees. It's actually a right angle. Likewise, those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as interangles. In addition, those two angles, they are located on the left side of the straight line AE. Because again, those two angles are both located on the left side of the straight line AE, and therefore they are also defined as one-sided. So in total, those two angles are defined as one-sided interangles, and according to rule 16, the sum of two one-sided interangles is equal to 180 degrees. So I write it down. This is the missing angle, that is angle BAE. Plus this angle, that is a right angle. In total, the sum of those two one-sided interangles is equal to 180 degrees according to rule 16. So repeat again. The sum of the missing angle BAE plus the right angle, that is 90 degrees, in total it must be equal to 180 degrees according to rule 16, because they are defined as one-sided interangles. Here we subtract 90 degrees from this equation, and we get that the missing angle BAE, the size of the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. So she found out that the other missing angle BAE is also a right angle, according to rule 16, of course. This angle is a right angle. So she found out that inside quadrilateral ABFE we have four right angles. And according to rule 5, any quadrilateral that has four right angles must be this rectangle if not a square. So let's quadrilateral ABFE is rectangle because it has four right angles. So write it down. This quadrilateral ABFE is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its side, in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side FB, but AE is edge, therefore FB must be also equal to edge. What is the length of the missing 97 FC? For the drawing, it is very easy to see that FC in total equals to DC minus DE minus EF. Again, FC equals to DC minus DE minus EF. So write it down. FC equals to DC minus DE minus EF. So FC in total equals to DC. DC is 44 minus DE. DE is X minus EF. EF is 16. So in total FC equals to 44 minus 16 is 28 minus X. So FC equals to 28 minus X units in its length. In the next step, I'll copy the right triangle BFC in the new page and we'll implement the Pythagoras theorem in this right triangle BFC. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle BFC that I covered from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, equals to BF squared plus FC squared. So I write it down. This will be equation 2. BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. The hypotenuse BC equals to 25, therefore BC squared is 25 squared, that is 625, and it equals to BF squared. BF is 8, therefore BF squared is 8 squared, plus FC squared. FC is 28 minus x, therefore FC squared is 28 minus x squared. So in total, we found out that according to equation 2, 625 equals to x squared plus 28 minus x squared. So here we'll open the brackets on this side of the equation 2, and you get that according to this equation 2, 625 equals to x squared plus 28 minus x squared. 28 minus x squared equals to 28 squared, that is 874, plus x squared, minus 2 times 28 minus x is minus 56x. So here we subtract 625 from this equation 2, and we get that after we subtract 625 from this equation 2, in this side of the equation we left with nothing, that is to say 0. In the other side of the equation we have x squared plus x squared minus 56x, and 874 minus 625 is equals to 159. So today we found out that according to equation 2, 0 equals to x squared plus x squared minus 56x plus 159. So here we add 56x to this equation 2, and we get that here 0 plus 56x is 56x, and it is equals to x squared plus x squared plus 159. So I repeat again, we actually found out that according to equation 2, x equals to x squared plus x squared plus 159. According to equation 1, we have already found out that x squared plus x squared equals to 289. Therefore, we can substitute x squared plus x squared in this equation 2 by 289 from equation 1. We'll do it now, and we get that according to this equation 2, (56x) equals to x squared plus x squared equals to 189 according to equation 1 plus 159. So in total we found out that according to this equation 2, 56x equals to 289 plus 159 is equal to 448. So we found out that according to equation 2, 56x equals to 448. Here we divide this equation 2 with 56. So again that according to this equation 2, x equals to 448 over 56. 448 over 56 is 8. So in total we found out that x equals to 8 units in its length. According to equation 1, we found out that 8 squared plus x squared equals to 289. If x is 8, it means that x squared is 8 squared, that is 64. So we can substitute x squared in this equation 1 by 64. We do it now, we get that according to this equation 1, 8 squared plus x squared and x squared is 64 equals to 289. Here we subtract 64 for this equation 1, so we get that 8 squared equals to 289 minus 64 is 225. So here we take a root out of this equation 1, and finally we get that h equals to the square root of 225. The square root of 225 is 15. So the height edge of trapezoid ABCD is equal to 15 units in its length. The height edge of trapezoid ABCD is equal to 15 units in its length. Our mission is to find out the area of this trapezoid ABCD. As I already mentioned before, we already found out actually that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus CD times the height, that is h, over 2. So in total, the area of trapezoid ABCD is equal to AB, that is 16, plus CD, that is 44, times the height h is 15, divided by 2. So the area of trapezoid ABCD in total is equal to 16 plus 44 is 60 times 15 divided by 2. 60 over 2 is 30, so in total this expression equals to 30 times 15. 30 times 15 is 450. So if I found out that the area of trapezoid ABCD is equal to 450 square meters. So repeat again. If I found out that the area of this trapezoid ABCD is equal to 450 square meters. So finish with the second question. In the next step, and so as the lecture, we start with the first question, of course. Our mission in the first question is to find out the area of this circle. So in the drawing we have a circle, and we have also, this is the common sum point P. From this common sum point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have also the right angle ACP. This angle is the right angle. The right angle ACP cuts the circle at 2 points, at point A and this point. We also know that the length of side CP of the right angle ACP is 4 units. This is 97 BC, that is equals to 1 unit in its length. Again, our mission is to find out the area of this circle. So first of all, we can implement here rule 2. Well, because for this connection point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB according to rule 2. And again, according to rule 2, the length of tangent PA is equal to the length of tangent PB. But it is given as a question that PB in total equals to 4 plus 1, that is 5. So we can write here that PB equals to 5, and from this equation PA equals to PB equals to 5, we will derive that PA is also equal to 5 units in its length. Is equals to 5 units in its length. Here PA is equal to 5 units in its length. In the next step, I copy the right triangle ACP in your page, and you measure the Pythagoras theorem in this right triangle, triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, this is the right triangle. This is the right triangle ACP that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equal to AC squared. AC is the missing side, so we leave it as it is, so it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, you should find out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and finally found out that AC squared equals to 25 minus 16 is 9. So AC squared equals to 9. Here we took a root out of this equation, and finally found out that AC equals to the square root of 9, that is 3. So AC equals to 4 units in its length. This is side AC that equals to 4 units in its length. So here AC equals to 3. In the next step, we define the center of this circle. This point O. We also define the radius of this circle as x. In the next step, we join points O and B together by side line. What is the definition of right side OB? Right side OB starts from the center of the circle and then at point B, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OB is the radius of the circle, that is equals to x according to our definition. Here we can implement rule 1, because we have the radius OB that is equals to x. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given as the question that PB is a tangent. So PB is a tangent, it is absolutely a straight line. PB is a straight line. So if we focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle plus this missing angle. In total, it must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. From this point O, we draw perpendicular on AC. Again, from point O, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, we created the quadrangle OECB. Inside quadrangle OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its side. So inside quadrangle OECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 integers must be its rectangle front a square. So we relate to quadrilateral OECD is rectangle because it has 4 integers. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OECB side OE must be equal to the opposite side CB. But OE is 1, CB is 1, therefore OE must be also equal to 1. Likewise, according to the sum rule, in the sum rectangle OECB, side OB must be equal to the opposite side CE. But OB is x, therefore CE is also x. What is the length for the missing last segment AE? Last segment AE is equal to AC minus CC. Again, AE equals to AC minus EC. So A equals to AC that is 3 minus EC that is x. So in total A equals to 3 minus x units in itself. Again, A equals to 3 minus x units in itself. In the next step we join points O and A together by third time. OA is of course the radius of this circle that is equal to x. In the next step we copy the right triangle OAE in the new page and we implemented the Pythagoras theorem with this right triangle OAE. Actually, this is the right triangle OAE that according to the original theorem, and according to the Pythagoras theorem, this right triangle OAE, this right triangle OAE, OA square equals to AE square plus OE square. Again, repeat again, OE square, OA square equals to AE square plus OE square. OA is x, therefore OA square is x square, and it is equals to AE square. AE is 3 minus x, therefore OE square is 3 minus x square, plus OE square. OE is 1, therefore OE is 1, therefore OE square is 1 square, that is 1. So in total, we actually found out that x square equals to 3 minus x square plus 1. So x square equals to 3 minus x square. 3 minus x square is equal to 3 square, that is 9, plus x square, minus 2 times 3 times x, that is minus 6x, plus 1. Here we have x square on both sides of the equation, so x square will get cancelled. After I cancel x square, on this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in conclusion, I found out that 0 equals to 10 minus 6x. Here we added 6x to this equation, and finally found out that 6x equals to 10. Here we divided this equation by 2, and finally found out that 6x over 2 is 3x, equals to 10 over 2 is 5, so 3x equals to 5. Here we divided this equation by 3 and finally found out that x equals to 5 over 3 units in its length. So we found out that the radius x of this circle is equals to 5 over 3 units in its length. Our mission is to find out the area of this circle. The area of any circle is equals to pi times the radius of the circle squared. And again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle will be equal to pi times the radius of our circle squared. The radius of our circle is x. Therefore, the radius squared is x squared. So in total, the area of our circle, that is the area that we are looking for in this equation, is equal to pi x squared. We just right now found out that x equals to 5 over 3. If x is 5 over 3, it means that x squared is 5 over 3 squared. So in total, the area of our circle will be equal to pi times 5 over 3 squared. So it is pi times 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total we should find out that the area of this circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of this circle is equal to 8.727 square units. We finish with the first question. In the next step, I present to you the second question and we solved it. Our mission in the second question is to find out the area of this trapezoid ABCD. It is given us the question that side AB equals to 16 units in its length, side AD equals to 17, side BC equals to 25, and side DC equals to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. Actually, the area of any trapezoid is equals to the sum of its two parallel bases times the height over 2. Repeat again, the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. In our trapezoid ABCD, the two parallel bases are AB plus DC. Therefore, the area of this trapezoid ABCD must be equal to AB plus DC, that is the sum of its two parallel bases, times the height, that is h over 2. Repeat again, the area of our trapezoid ABCD is equal to the sum of its two parallel bases, that is AB plus DC, times the height h over 2. The height h must be 90 degrees with the two bases AB and DC. In order to find out the area of this trapezoid ABCD, we did a construction. That is to say, from this point A, we draw perpendicular on DC. Again, from this point A, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. Likewise, we define the length of line 7D is x, and the length of line 7AE is h. AE, that is equals to h according to our definition. AE is also the height of trapezoid ABCD. Why AE is the height? Because of the fact that AE creates 90 degrees with the base DC. Therefore, AE is the height of trapezoid ABCD. In the next step, I copied the right triangle AED in the new page and implemented the Pythagoras theorem on this right triangle AED. Actually, this is the right triangle AED that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle AED, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289, and it equals to AE squared. AE is h, therefore E squared is h squared, plus DE squared. DE is x, therefore DE squared is x squared. So in total, according to equation 1, we actually found out that x squared plus x squared equals to 289. In the next step, we did another construction. That is to say, from this point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. So now, here we can implement rule 16 on our drawing. Why? Because we know that AB is parallel to DC, and those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as center angles. In addition, those two angles, they are both located on the right side of the straight line BF, and therefore they are also defined as one-sided. So in total, those two angles, they are both defined as one-sided interangles. And according to rule 16, the sum of two one-sided interangles is equal to 180 degrees. So I'm going to click on rule 16. So according to rule 16, the sum of one-sided interangles is equal to 180 degrees. So those two angles 4 and 5, they are both defined as one-sided interangles, and according to this rule 16, the sum of those two angles is equal to 180 degrees. That is to say, angle 4 plus angle 5 is equal to 180 degrees according to this rule 16. Likewise, those two angles 3 and 6, they are both defined as one-sided interangles, and therefore according to this rule 16, the sum of those two angles is equal to 180 degrees. That is to say, angle 3 plus angle 6 is equal to 180 degrees according to this rule 16. So we can actually implement rule 16 in our drawing. Why? Because in our drawing, so as I mentioned before, Those two angles they are both defined as one-sided interior angles, and according to Rule 16, the sum of those two angles must be equal to 180 degrees. So this is a right angle, and this missing angle is angle ABF. And according to Rule 16, the sum of those two angles in total must be equal to 180 degrees. So repeat again. According to Rule 16, the missing angle ABF plus the right angle in total must be equal to 180 degrees according to Rule 16. Here we subtract 90 degrees from this equation and finally found out that the size of the missing angle ABF is equal to 180 degrees minus 90 degrees is 90 degrees. So the size of this missing angle ABF is equal to 90 degrees. Likewise, those two angles they are both defined as one-sided interior angles, exactly for the same reason that those two angles are defined as one-sided interior angles. So I repeat again, those two angles they are both located between the set line, the parallel lines AB and DC, and therefore they are defined as interior angles. In addition, those two angles they are both defined as one-sided angles because they are both located on the left side of the straight line AE, and therefore they are defined also as one-sided angles. And so in total, those two angles are defined as one-sided interior angles, and according to Rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So according to Rule 16, this is the missing angle BAE plus this angle that is right angle. In total, it must be equal to 180 degrees. The missing angle BAE plus the right angle in total it must be equal to 180 degrees according to Rule 16. Here we subtracted 90 degrees from this equation. And finally found out that the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle BAE, it is equal to 90 degrees in its size. So in total we found out that inside quadrilateral ABFE we have 4 right angles. And according to Rule 5, any quadrilateral that has 4 right angles must be at its right angle if not a square. So we relate to quadrilateral ABFE as right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side FB. But AE is 8, therefore FE must be also equal to 8 units in its length. What is the length of the missing line segment FC? From the drawing, it is very easy to see that FC in total is equal to DC minus DE minus EF. Again, FC equals to DC minus DE minus EF. Repeat again, FC equals to DC minus DE minus EF. So FC equals to DC, that is 44, minus DE, that is X, minus EF, that is 16. So in total, FC equals to 44 minus X minus 16. 44 minus X is 28. So in total, this expression is equal to 28 minus 6. So we found out that FC equals to 28 minus 6 units in its length. The next step, we copied the right triangle BFC in the new page and we implemented the Pythagoras theorem on this right triangle BFC. So actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of their product, must be equal to BF squared plus FC squared. BC is 25, therefore BC squared is 25 squared, that is 625, and it is equal to BF squared. BF is S, BF is H, therefore BF squared is H squared, plus FC squared. FC is 28 minus X, therefore FC squared is 28 minus X squared. So in total, according to equation 2, I should found out that 625 equals to H squared plus 28 minus X squared. So 625 equals to 8 squared plus 28 minus x squared. 28 minus x squared equals to 28 squared, that is 874, plus x squared minus 2 times 28 minus x, that is minus 56x. Here we subtract 625 from this equation. If you know that 625 minus 625 is 0, and it is equals to 8 squared plus x squared minus 56x, and 874 minus 625 is equals to 159. So in total we found out that 0 equals to 8 squared plus x squared minus 56x plus 159. Here we added 159 to this equation, equation 2, and finally found out that according to this equation, equation 2, 56x equals to 8 squared plus x squared plus 159. According to equation 1, 8 squared plus x squared equals to 289. Therefore, we can substitute x squared plus x squared in this equation, equation 2, by 289. We did it, and we found out that according to this equation, equation 2, 56x equals to 8 squared plus x squared is 289, according to equation 1, plus 159. So in total, we found out that 56x equals to 289 plus 159. 289 plus 159 is equal to 448. So in total we found out that according to this equation, equation 2, 56x equals to 448. So here we divided this equation, equation 2 by 56, and finally found out that according to this equation, equation 2, x equals to 448 over 56 is equal to 8. So x equals to 8 units instead. According to equation 1, we already found out that x squared plus x squared is equal to 289. X is 8, therefore x squared is 8 squared, that is 64. Therefore, we can substitute x squared in this equation, equation 1, by 64. We did it, and we found out that 8 squared plus x squared, that is 64, is equal to 289. Here we subtracted 64 from this equation, equation 1, and finally found out that 8 squared equals to 289 minus 64 is 225. So in total, we found out that 8 squared equals to 225. Here we took a root out of this equation, and finally found out that h equals to the square root of 225. The square root of 225 is 15. So we found out that h, that is the height of trapezoid ABCD, is equal to 15 units in its length. This is the height h of trapezoid ABCD, and it is equals to 15 units in its length. Our mission is to find out the area of this trapezoid ABCD. The area of this trapezoid ABCD is equals to the sum of its two parallel bases, that is to say AB plus DC, times the height, that is edge over 2. Repeat again, the area of this trapezoid ABCD, that is the area that we are looking for in this question, is equal to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is edge over 2. So in total, the area of trapezoid ABCD is equal to AB, that is 16, plus CD, that is 44, times edge is 15 divided by 2. 16 plus 44 is 60, so it is 60 times 15 divided by 2. 60 over 2 is 30, so in total this expression is equal to 30 times 15. 30 times 15 is 450. So in total, we found out the area of this trapezoid ABCD is equal to 450 square units. Okay? Thank you very much.